Okay, so pretty much all of this time we've been working with, given a function, finding the derivative of that function. We're just going to focus on first derivative of that function. And we do that by applying our derivative rules. So last week when we talked about the definite integral as this area underneath the curve, we want to keep that in mind because that's part of this too. And what that gets at is the antiderivative. So what we're going to be doing is we've been working in this one direction the whole time, and now what we're going to do is flip it. So what we're going to have is we're going to be given the derivative function, and what we want to do is find our original function. So knowing the derivative, what was our original function? So with this, we're going to reverse those derivative rules. And what we're doing here is we are taking the antiderivative. And what we'll have is a few scenarios, so that integral notation is going to connect to the antiderivative. We can have a definite integral or an indefinite integral. So definite integral we saw last week where it was defined over an interval, and that would be the equivalent of finding the area under the curve. We're also going to talk about the indefinite integral, which is going to be a case of just finding this antiderivative function. So let's talk about a little example here. So say we wanted to find f of x if f prime of x is 2x. So what we're doing is we're starting with our derivative function. And what I want to know is what is our original function. So some things I'm thinking about here is I have this 2 out front. And when we take the derivative, in order to get to there, that value out front would come from an exponent. So what I could see is, if I fill in the blank here with x squared, the derivative of x squared is exactly 2x. So this starts the process of the antiderivative. I have one extra piece here, and it's the fact that x squared, we could have a constant adding on. For example, if our original function was x squared plus 3, or if our original function was x squared minus 5, the derivative of both of those functions is 2x. So the idea is that there's this constant that we can add on at the end. It can be positive or negative, it could be a decimal, it could be a whole number, all sorts of possibilities, but the idea is that if we're adding a constant, when we take a derivative, it turns into 0. So something we're going to want to add on whenever we take an antiderivative is plus c to represent this constant that could be adding on at the end. A lot of times we'll just leave it like that. So f of x is x squared plus c, where we don't know what c is. If they give us extra information, then what we can do is find c and have an actual value to go there. So we'll look at a few of those different scenarios. So an antiderivative of a function f of x is any function f of x with a capital F. So this is where the notation gets a little tricky, where capital F prime of x is equal to little f of x. So basically, this notation can get really tricky, but the idea is that we have this antiderivative function and a derivative function working together. We can represent the antiderivative is also called the indefinite integral. So the indefinite integral is where we have our integral symbol without any interval attached to it. So it's just the integral of some function dx, so that we can see which variable we're anti-differentiating with respect to. And that's going to be some antiderivative function. So up above, how we worked with this question, how I could have asked this is writing the indefinite integral of 2x dx, that would be the same as asking what is the antiderivative of the function 2x. And the result would be x squared plus c. Okay, so with this section, we're reversing rules, and with that, it can boggle the brain a little bit because we've been training our brain to go one way all term so far, and then we need to reverse it. So in this section, I'm just going to kind of talk through how we can think about these antiderivatives, but just like how we have our derivative rules, in the next video, we'll get the formulas that we can kind of rely on. But I want us to think about these antiderivatives before applying the rules. So let's say I wanted to find, so the notation here is indefinite integral e to the x dx. How I read that to myself is the antiderivative of e to the x dx. The dx, again, just tells me what variable we're working with, so I'm focusing on taking the antiderivative with respect to x. Okay, so what I'm doing is I'm looking at the function e to the x power, and what I want to know is what did I need to take the derivative of to get to e to the x? Now, e to the x is really nice because the derivative of e to the x is just e to the x. So if we got that as the derivative, that means we must have started with e to the x. So taking the derivative of e to the x would have gotten us to e to the x. Now, the thing that I need to add on here is a plus c. We need that plus c to show that there could be some constant adding on at the end there. We don't know what it is without any further information, but there could be a number adding or subtracting on. Okay, so with that, let's look at some cases with the power rules. So, this one is missing a dx here. All right, so the antiderivative of negative 12x to the 5th power plus 3x squared. So with the powers, what we're going to do when we're taking the antiderivative, so when we took the derivative, the exponent bumped down. We took one away. If we're going in the reverse direction, that means we're bumping it up. So every exponent that we have, we're going to bump it up by 1. So what I know is where I have x to the 5th, the antiderivative is going to involve x to the 6th. And where I have x squared, bump it up by 1, so we're going to have an x cubed involved. Now that I can see my x to the 6th here, if I think about taking the derivative, there's a 6 that's going to come out front. So let's say I just leave the negative 12 right there. So if I take the derivative right now, I would have this 6 times negative 12, which we don't want, that'll be too big if I'm supposed to end up at negative 12. So what I can do here is divide out that exponent of 6. So this setup right here is going to make it work so that I don't have to evaluate that numerical coefficient right away. I can just leave that negative 12 there. But it's that whatever exponent we kind of bump up to for the antiderivative, we need to divide out that exponent because of that property of when we take the derivative, that 6 is going to come out front and we bump it down to a 5 in the exponent. So again, it's this just kind of reversing it around. So with 3x squared, so we know we're going to have an x cubed, I'm just going to keep that 3 there out front as the numerical coefficient. But the idea is that when I take the derivative, I'm going to have a 3 from that exponent coming out front to multiply. So just to get everything to even out, I'm going to divide by 3. So I end up with negative 12x to the 6th divided by 6 plus 3x cubed divided by 3. And as always with these, plus c at the end there. And now we can simplify. So I'm going to simplify, and that'll be a negative 2x to the 6th power plus x cubed plus c. Now, we have, like I've been saying a few times, all this term we've been looking at taking the first derivative. When you get to the end here, you can always check. You can check your answer by taking the derivative of our function. So let's say I did d dx of this negative 2x to the 6th power plus x cubed plus c. So if I take the derivative here, I'm going to have a negative 2 times 6, so negative 12, x to the 6 minus 1, which is 5, plus 3 times x squared, and then the derivative of c just turns into 0. So with that, I can see that I end up with that function that was inside the antiderivative. So that would just confirm for me that I did in fact take the antiderivative correctly. Okay, let's look at a case with negative exponents. So again, with this power rule, and where we have 10x, let's just put an exponent of 1 right there to see the kind of placeholder. So these powers are going to bump up by 1. So all of these powers are going to bump up by 1. So plus 1, plus 1, plus 1. So where I have 10x, I'm just going to rewrite that as 10x squared. And I need to keep in mind that I need to divide away that same exponent that we ended up with. So if I have x squared, I'm going to be dividing by 2 so that it works out. And I'm going to go plus 6x, and then where it was negative 3, now it's going to be a negative 2. And then I'm going to divide by that same exponent so that when we take the derivative, it kind of cancels itself out. And then we're going to have minus 3x to the negative 4 plus 1, so negative 3, and then divide by that same exponent, negative 3, and to finish it off, plus c at the end. We can't forget it. And then we can simplify. So 10 divided by 2 is 5, so we're going to have 5x squared, positive 6 divided by negative 2, so negative 3x to the negative 2, and then negative 3 divided by negative 3, so positive 1x to the negative 3 plus c. And that would be done there. Again, we could double check by taking the derivative, so 5x squared would get us to 10x, negative 3x to the negative 2 would get us to positive 6x to the negative 3rd power, and x to the negative 3 would get us to the negative 3x to the negative 4th. All right. Last one here, a bit tricky, but we can do it. So with this, first thing I'm going to do is change it to rational exponents. So we have 16 cube root x, which is the same thing as 16 times x to the 1/3 over 3. And then we're going to have minus 15, and the 4th root of x is going to be x to the 1/4. And then that's being divided by 4 dx. Okay, so each of those exponents are going to bump up by 1. So when we take the antiderivative, I'm going to have 16x, and then 1/3 plus 3 over 3, so 4/3. And then I'm going to keep that 3 that was originally in the denominator still in the denominator. But what's going to happen is we're also going to be dividing by this 4/3. So how I can write that is that 3 in the denominator, it's getting multiplied by 4/3. So that's how we can see that division of the exponent there. And I'm going to have minus 15x to the now 5/4. And then I'm going to keep that 4 in the denominator, but then I'm going to have that multiplied by that exponent of 5/4. So what's nice about these is they have a nice cancellation. So like with that first one, I'm just going to have 4 left over in the denominator. So 16 divided by 4 is 4. X to the 4/3 is the same as cube root of x to the 4th. And then we'll have minus 4 times 5 over 4, which just leaves us with 5. So 15 divided by 5 will leave us with 3. And then it's a 4th root of x to the 5th. And I almost forgot plus c. We'll have some constant at the end. So this is a rule we're going to get used to. It's kind of reversing our power rule for when we want to take the antiderivative.